queuing theory for Node developers. So give him a warm round of applause.
Can you hear me? Yeah, you can. Great. So my name is Avishai Ish-Shalom, as he said. Nukenberg on Twitter, if you want to follow me or talk to me after. This is the best way to get to me. So we're talking about Q theory today, which is a mathematical, actually statistical theorem that was originally conceived in the beginning of the 20th century for optimizing what was then known as switchboard for telephones. So in the old days, when you pick up a phone, someone would answer on the other end of the line. You would have to ask that person to connect you to someone, to whoever you want to call, and there would be people on a giant switchboard, like an actual physical switchboard, that had to physically connect you to whoever you wanted to speak with. And the question was, how many people did you need to employ at a certain time in order to keep the waiting time for the operator down? So this is why originally they developed this, but now, today, we use Q theory for a very large number of things in the industry, logistics, and also in software. So this has a lot to do with software performance. So why are we having this talk? How is this relevant to Node? So basically, this is the basic structure of Node.js. And when you have this event loop that's standing in the middle of everything, it's connected to a bunch of other things on the periphery. So you have clients that are talking to the server using some socket, and between the clients and the socket, there's a queue, usually operated by the kernel. And when you talk to a database, so between the Node.js process and the database, there's a queue. And there's another queue between your code and the event loop, which we'll discuss in a bit. But the point is that you have queues everywhere. Everywhere in software and in computers, you have queues lying around, and this means that Q theory is something fundamental that we need to understand in order to understand computer performance in general. So just keep this in mind, and let's dive into statistics a little bit. So the world is made of distributions. So when you say something like, my height is 1 meter 70 centimeters, that's not an actual number. It depends on the measurement, when you measure, how many times you measure. Every time you measure something, you would get a slightly different result. And yes, all of the results might be in the same range, but they're not the same. What you would get is a distribution of results. And this actually has a lot of impact on how things behave. So, of course, every distribution has some width, and there's no one number that can capture the shape or the width of the distribution. We need several aggregates in order to understand what is the shape or behavior of a distribution. That's very important. A lot of times we talk about stuff like mean or average, and that's, in many cases, bullshit. Why is it bullshit? Because it doesn't capture the variation or how wide the distribution is. And think about variation. There's a lot of metrics for this. The known ones is standard deviation or variance. There's other ones like interquartile distance or mean average deviation. It doesn't really matter which one you use. They're good for different things. But the point is that when you have this width of the distribution, it really, really matters. And we'll talk about that in a bit. So distributions in general are infinite. But the systems that we deal with, computers, they're not infinite. Every time that we get a number in our computer, if it's an integer, it cannot be larger than maximum integer. If it's something else, there's always a limit. Why? Because memory is not infinite. So what do we do with infinite numbers that don't fit in our memory? We trim them. This is how we get errors, basically. We just we have cutoffs when something is out of range. And we need to remember this because distributions are infinite, which means that we will always get some errors or something that wraps around or anything of that sort. So the thing about the variation is it's very easy to raise it, but very hard to reduce it. And this matters why? Because variability has a very large effect on utilization. So think about this example. You're driving from Jerusalem to Tel Aviv. It takes, the train takes maybe 40 minutes nowadays, and you have to be there in 2 hours, let's say. But the problem is the train doesn't have an exact time that it takes from Jerusalem to Tel Aviv. Sometimes it takes 40 minutes, maybe it takes 40 minutes on average, but it's sometimes delayed. And of course, the average delay is maybe 5 minutes, but the P99 of the delay is 60 minutes. So if you have to be in Tel Aviv in 2 hours, and you have to be there with an SLA of, let's say, 99 point something %, this means that you have to be early at least 1 hour. So most times, that time that you'll just be waiting for the train, and that time will be wasted. But you still have to spend that time to get that probability of reaching your destination on time. And this is why in computer performance, when you have large variability, we're wasting a lot of resources just to keep an SLA. So that's basically the problem of variation. And high variation has impact in a lot of places in our systems. It destroys utilization, and of course, whenever you have something like group latency, maybe fork join or anything like that, or map reduce, then it means that performance follows the high percentiles instead of the average or the median. Computer satisfaction, there's a very big difference between aggregate effects. Think about load, for example. The server feels the impact of all the clients together, whereas every client individually feels the impact of only its transaction. So when we're measuring, for example, user experience, we're interested in the high percentiles, and when we're measuring load, we would be interested in sums or means, averages, that kind of stuff. So very different aggregates. And of course, disasters. What are disasters? It's basically stuff that's an error. What is an error? Like we said before, it's something that's like way off in the distribution. So it follows the high percentiles, basically outliers. That's the major cause of disasters. And of course, when something fails, what do? We retry. And retry basically increases the load. So failure demand. Failure demand is demand that was generated by a failure to do something in the first time. So for all those reasons, variance is the biggest challenge that engineers have in the back end. Okay? We try to reduce variance wherever possible. Not always it's possible. Sometimes we actually use variance in our advantage. For example, in hardware, we often use different types of hardware to protect against correlated failures. But in general, variance is the engineer's enemy. This is something that we combat every day. So now that we understand a little bit about statistics, let's talk about queues. So what is a queue? This is the basic structure of a queue. Basically, we have a service center that is doing some work, servicing some load. And we have incoming work, and that work is being queued on a buffer, some storage space. And when we talk about latency, latency is actually composed of two things. It's composed of the time that it took to service the request, actual work, and the time that we spent waiting in the queue. Okay? So the wait time plus the service time, this is the latency that we observe. Okay? And the question is then, how long are we going to wait in the queue? So when something is blocked in the queue, it doesn't matter why, what's going to happen is head-of-line blocking. Okay? So the head of the line, everything in the queue, except for the work that's currently being serviced, is going to wait. And this means that even if one particular job is being delayed for whatever reason, okay? And remember, we're talking about statistics, so there's some chance that this work happens to be larger, or maybe the CPU is busy right now, or maybe you have garbage collection. Doesn't matter. There's going to be some reason for this work to be on the far end of the distribution, and then it's going to delay everything in the queue. Okay? So this means that even if you have one job that is in the high percentiles, it's going to have non-proportional impact on the latency of all other requests that are supposed to be independent, but actually are not. Wait, what's going on here? There's a slide missing. Okay, here we go. So this is basically what's going on inside of a queue. This is like the microscopic view of a queue. Okay? So the load that is going into the system, it's not uniform, okay? It has some distribution. In this model, we use the Poisson distribution for the incoming load, which basically means that the rate is slightly different between moments, okay? Sometimes you get a bunch of tasks, sometimes you get less tasks, and so on. And on the other hand, on the other side, we have the service time, which is also not uniform. In this case, the exponential distribution. So sometimes it takes more time to process. Maybe we got a large JSON. Sometimes it takes less time. And this is like the microscopic view of what's going on in the queue. This is basically the queue length. And what you can observe here is that although this red line is the mean or the average length of the queue is often much higher than this. It's very spiky in a way. And this is the general behavior of queues. What we can observe is that queues are almost always empty or either almost full. But it's very hard to catch them in the middle. They start being full very, very fast. And why? Because of head-of-line blocking. Whenever something is blocked in the queue for whatever reason, immediately you will get a delay. So what is this happening? Okay? It's a lose-lose situation. If, for some reason, the service center is starved, meaning that there's no work in the queue, we cannot save that time for later. The service center is going to sit there doing nothing. We're going to see like 0% CPU. Nothing will happen, and we can't bank that time for later. But if, on the other hand, we got some spike of load, or maybe some work is larger and needs to be processed, and we need to use the service center for longer, then we lost. There's going to be a spike, and the queue is going to fill up very, very fast. So it's basically a lose-lose situation, and this is the general problem with queues. So when we plot the queue size, or the queue length, or the latency, versus the utilization, we can see that it depends on the utilization. The higher the utilization of the service center, so it goes from 0% to 100%, the higher the latency will be, but it's not linear in any way. You can see that it starts to rise very, very fast when we approach 100% utilization. So even on 70% utilization, you're going to get twice the amount of latency that you normally have. So if a service center, let's say that your requests have an average of 10 milliseconds, with 70% utilization, you're going to observe 20 milliseconds latency. And when you approach 90%, you can see that it's going up to infinity. So the lesson here is that you cannot run systems close to the edge of the capacity. And the more utilization you're going to have, the more dangerous it's going to be and more sensitive it's going to be to problems. So what do we need to do? We need to keep our systems in lower utilization. Okay? Basically, we run systems on purpose on, let's say, 70% or 50% utilization, depends on the particular system. Okay? So, okay. What happens when a queue starts to fill up? Okay? So if we have a delay, queues start to fill up, and if they're unlimited for whatever reason, we're going to have problems, because remember, computers are not infinite. So first of all, we're going to have memory pressure, because queues are basically stored in memory. And memory pressure means garbage collection, could be garbage collection storms even, could be out-of-memory errors and process crash and stuff like that. But even before that, we're going to observe high latency as we start to drain the queue very slowly, and it takes time. And when something waits in the queue long enough, it can be stale. Okay? Maybe the client has timed out, and now you're servicing work that actually doesn't mean anything anymore, and you're just wasting your resources. So never, ever use unlimited queues. What's the problem? Not all of the queues are in our control. A lot of them are actually owned by the operating system, by Node.js, by drivers, and so on. And yes, a lot of them are unlimited because reasons. Mostly because people don't notice. But I've actually caught several bugs in several drivers because of this. So remember that utilization also fluctuates, which is another big problem. So we said before that if you run systems on close to the edge, let's say that you have 10 times the latency amplification. So in 50% utilization, a 10% change in utilization is only going to take you from 0.5 to 0.55, which means that latency will rise by about 10%, which is not much. But if you're running at 90% utilization, and utilization fluctuates by 10%, it's going to take you to 0.99, which basically means you're going to rise from 10x the amount of latency to 100x, which is basically an outage. Okay? So you cannot run systems close to their capacity edge. Okay? And if you do, you have to make sure that to keep the variation and utilization very much under control. We're going to talk about that in a minute. Okay? But this means we have to cap high load somehow, using load shedding or backpressure, which we'll talk about in a bit. So I'm going to go back to this slide here. So this slide here, what it basically says, this formula, you can ignore it if you want. The only thing that's important here are the two coefficients here. Those coefficients denote the variation of both the service center and the load. And you can see that the wait time is proportional to the variation squared. So the higher the variation, the more latency you're going to get, and it's going to be very, very aggressive. So basically what this means is that if you see in this graph here, this line over there on the left, this is the line of the high variation trend. And you can see that this line is much, much worse than all the other lines. Basically, it means that utilization is going to be, that latency is going to be much more sensitive to utilization the higher your variation is. So you want to keep variation down as much as possible. And if you have high variation, then also your percentile curve is going to be much, much worse. So let's go back to Node.js, okay? So we have a lot of tasks that are supposed to be independent in Node.js. Different requests, different microtasks. If you don't know what a microtask is basically every callback or every await or promise that you have. It's a microtask, different microtasks. And they're supposed to be independent, but they're not. Why are they not independent? Because they're sitting in a shared queue. All of them are sitting in the shared queue, waiting for the same work center, and this means that they're going to be impact between different tasks on each other. Okay, so we have a lot of shared queues in the system. We have disks, we have CPUs, we have thread pools. Yes, Node has a shared thread pool as well. We have connection pools, database logs, sockets, and of course, the event loop, which is shared for everything in Node.js. And when we have different phases we have different phases on the event loop, which have different queues, but they all share the same event loop. So it's a shared resource, and it's going to impact even between different phases of Node.js. And of course, head-of-line blocking, as I explained, means that there's going to be cross-task interaction, and various, of course, makes everything much, much worse. So an executive summary of what's going on in queue tiering. Basically, high utilization means high latency, and it's rising very, very fast. It's not linear. Never use unlimited queues, okay? And it really depends on what you want. If you have interactive systems which interact with a user or something like that, and you want to keep latency down, then you want to use short queues. On the other hand, if you want to keep utilization high, then you don't care about latency. For example, batch systems, then use long queues. And maintaining proper utilization is key for computer performance. Now let's talk about Node.js. This is the basic structure of Node.js and the event loop, okay? And the event loop has different phases and basically processes different types of callbacks at different phases of the event loop. So your code mostly runs in the poll phase and here, okay? And basically in response to sockets or HTTP requests or stuff like that. And when you use setImmediate, then it's running in this phase here, the check setImmediate, the immediate phase. And when you use something like set interval or set timeout or something like that, then you're running at the timers phase, okay? So this is basically where your code is running. And the thing is that every one of those phases has an individual queue. And the sockets, of course, also has an operating system queue, okay? So it's basically something like this. This is like we took one phase and we enlarged it. So when your code is running and you have some callback, maybe you're doing a wait sync or maybe it's promise then, doesn't matter. The callback goes into the event callback queue, okay? And it's waiting there until the event loop has drained the queue enough so it gets to that particular callback and runs it. But it takes time. How much time? Depends on how busy the event loop is, okay? And this is what is known as event loop lag. You can measure it, it's very easy. On older versions of Node, you had to measure it using a timer, but nowadays, I'm going to show this in a bit, there's a performance API which actually provides this kind of metrics, and you can observe the lag by yourself, okay? And similarly, when you send something to workers or to the thread pool, there's a callback queue between the event loop and the thread pool. Okay? And again, there's lag associated with that queue as well. It's going to take some time. You're going to have some latency. How much? Again, depends on how busy the thread pool is, or in other words, the utilization of the thread pool and the event loop. Okay? And what happens if this takes a long time, this processing of this queue? So Node.js doesn't move to the next phase until one of two things happen. One, the callback queue is empty, completely empty, and nothing is being queued anymore in that queue. Or second, you have reached a very large number of processed callbacks, which is basically the maximum amount of callbacks that are being executed in a loop, and in one loop iteration, and then Node.js will move to the next phase, okay? This has a very dire implication. If you encode too many callbacks in this queue, let's say you have some loop that, or recursion that keeps generating more callbacks, you're going to starve the event loop, and it will not advance to the next phase, which basically means that it will never reach the point where it pulls on sockets, for example, which means that you're not going to be accepting new HTTP requests, for example, or you're not going to execute new HTTP calls to external servers, or you won't be able to send requests to Kafka, or whatever network communication that you're doing. You're basically going to starve the network phase of Node.js. Okay? So what can cause this to be much, much worse? Anyone has a guess? What should you never, ever do in an event loop? Never block. You should never block the event loop. If you block the event loop, then the service center is going to be blocked. Latency is going to start rising very fast because the queues, remember, they're going to wait and wait and wait for something that will not be released in a very long time. Okay? So this is why you never want to block the event loop. Okay? So just a summary, this is mostly here for the slides. Basically, unlimited queues in the event loop because, yeah, you know. And you want to basically not starve the event loop as much as possible. Okay? And remember, a wait then process basically goes back to the callback queue and hogs the event loop. So how do we deal with this? Okay? What's our coping strategies? So first of all, never ever block. Okay? So what's common causes of blocking? CPU. CPU is always blocking, so if you do something that's CPU intensive in your code, that's going to block. Usual suspects, JSONs, very large, uncomplicated JSONs, very bad idea. Regular expressions, also a killer. Server-side rendering, also a killer. You get the point, okay? So what do? There's a number of models that can help with this. I've put some here, okay? Basically models that process in, JSON in parts or do this asynchronously. Or they offload to thread pools or remote processes or workers, also a very nice thing to do. When you are in doubt, when you have something very large that you need to do, you want to give Node.js a chance to advance to the next phase. How do you do this? You split into small microtasks and you defer. And when I say defer, I don't mean a wait, because that's basically going to re-enqueue, okay, in the same phase. What you do instead is you use set immediate, and basically you move the next phase of the work to the immediate phase, thereby unblocking the event loop and allowing it to proceed. But if you do this many times, then the immediate queue is also going to be hammered. So again, you have to limit the amount of work that you do. And of course, backpressure. So what is backpressure? Basically, the load that's coming in, that's forward pressure. And then internally, you have something that's going to be overloaded. Maybe the database, maybe the event loop, doesn't matter. You somehow need to propagate back this message and say to the load balancer or the web server, stop sending traffic, I'm overloaded. And then the client would also get this message from the load balancer saying, stop sending traffic, I'm overloaded. So you have to propagate back the pressure. This is why it's called backpressure. And how do we do this? There's two ways. TCP supports this by TCP backpressure, and HTTP supports this with the 429 status code and 503 status code, basically. Okay, so what do we do in Node.js to do this? So if you're very lazy, you can just limit the amount of HTTP connections that are going in with Express or Koa, and then they will apply TCP backpressure. Another way is you can limit or reject the requests when you're overloaded by measuring the event loop lag, and when the lag is too high, you just basically send back 503 or whatever you want to send. There's a model called Node2Busy that does this, but I wouldn't use it because it's like 20 lines of code, so why use a dependency for this? But just have a look. It's very easy. So what about metrics? So this is the metrics that you can use to get those numbers. So first of all, there's a new model in Node.js, I think from version 12 already, or even 10. And basically, you can get the event loop delay and the event loop utilization from it without a problem. Very useful. Highly recommended that you plot this. And of course, use this to reject work when you're overloaded. And of course, monitor the garbage collection, because this is a major cause of variation and low performance in Node.js. So, summary of what I've said in this presentation. First of all, never ever block the event loop. Don't do this. Try to break your processing into small microtasks and defer some of them to get more smooth performance in Node.js and not block the event loop or hog the queue for too long. And you want to monitor this, and if you have any kind of Node.js that is operating within the system, you want to apply backpressure to the web server and, of course, to the client, and maintain proper low utilization, otherwise your latency will start rising very, very fast. And whenever possible, reduce variation, because this is the key to get good performance and high utilization. So thank you very much. If you have any questions,